The sun, our planet's giant battery? Our sun is truly amazing. It sends a huge amount of energy to Earth. This energy arrives every single second of every single day. Think of it like a giant power station in the sky. It never runs out of fuel. The amount of solar power that reaches our planet is vast. It is far more than all the energy humans use. We currently use a lot of energy for our homes and industries, but the sun gives us about 10,000 times more than we need. This is a fantastic opportunity for us. Imagine if we could capture just a small part of this solar energy. We could power everything we do. Our lights, our computers, our factories could all run on sunshine. This is not a dream. It is something we can work towards. The sun provides this energy freely. We do not have to dig for it. We do not have to burn anything to get it. It is clean, and it is always there, shining down on us. This constant supply makes solar energy very reliable in the long term. The challenge is to collect this energy efficiently. We need good ways to turn sunlight into electricity. This is where solar panels come into the picture. They are the tools we can use. They help us tap into this incredible natural power source. Using solar energy can help us reduce our reliance on other fuels. These other fuels can be dirty and can run out. The sun, however, will be with us for billions of years. It is a steady and dependable source of power for our planet. So, the sun offers us a massive, clean, and endless supply of energy. It is like having a giant battery in space, always charged. We just need to build better connections to it. Learning how to do this effectively is very important. It could change how we live and how we treat our planet. Harnessing this power is a key step towards a sustainable future. This future would be less dependent on polluting energy sources. It is a bright prospect for everyone. Solar panels, catching the sun's rays. Solar panels are clever devices. Their main job is to catch sunlight. Then, they turn this sunlight directly into electricity. This process is called photovoltaics. It sounds complicated, but the basic idea is simple. Light energy is converted into electrical energy. Most solar panels use a material called silicon. Silicon is very common on Earth. It is the second most abundant element in our planet's crust. This means we have plenty of it to make solar panels. The way solar panels work is quite neat. They do not have any moving parts. This is a big advantage. Moving parts can wear out or break down. Because solar panels are solid and still, they can last for a very long time. Many solar panels can keep working for decades. They just sit there, quietly making electricity whenever the sun shines on them. This makes them a reliable technology for generating power. They require very little maintenance once installed. The conversion of sunlight happens inside special parts called solar cells. Many of these cells are grouped together to make a solar panel. When sunlight hits a solar cell, it excites tiny particles. These excited particles then start to move. This movement creates an electric current. This current is the electricity we can use. It is a direct transformation of light into power. There are no turbines spinning or fuel burning. It is a clean and silent process. So, solar panels are like silent guardians. They capture the sun's energy for us. They use a common material, silicon, to do this magic. Their lack of moving parts means they are durable. They can provide clean electricity for many years. This makes them a very attractive option for our energy needs. As we look for cleaner ways to power our world, solar panels offer a strong solution. They are a key technology for a sustainable energy future. The heart of the matter: how solar cells work. Let's look closer at a solar cell. It is the real worker inside a solar panel. Most solar cells are made from silicon, but it is not just plain silicon. There are two special types of silicon used. One type is called N-type silicon. It has some extra electrons, which are tiny negative particles. The other type is called P-type silicon. This type has tiny spaces where electrons could fit. These spaces are often called holes. These holes act like positive charges. These two types of silicon, N-type and P-type, are put together. They meet at a place called the p-n junction. This junction is very important. When the two types of silicon meet, something interesting happens. The extra electrons from the N-type silicon want to move. They move over to fill the holes in the P-type silicon. This movement creates an electric field across the junction. Think of this electric field as a gentle slope or a one-way street for electrons. Now imagine sunlight hitting the solar cell. Sunlight is made of tiny packets of energy called photons. When a photon with enough energy strikes the silicon, it can knock an electron loose. This happens in both the N-type and P-type layers. When an electron is knocked loose, it leaves behind a hole. So now we have a free electron and a free hole. These are called an electron-hole pair. They are the key to making electricity. The electric field at the p-n junction then does its job. It acts like a separator. It pushes the newly freed electrons towards the n-type side, and it pushes the holes towards the p-type side. This separation is crucial. Without the electric field, the electrons and holes might just find each other again. But the field keeps them apart. It forces them to go in different directions. This sets the stage for creating an electric current. Section 4. From sunlight to your light switch. The journey of solar electricity. Once the electrons are freed and separated, they need a path to travel. Thin metal strips are placed on top of the solar cell. These are often called metal fingers or contacts. These metal fingers collect the electrons from the n-type silicon. The electrons are now eager to move. They want to reach the holes on the p-type side, but the p-n junction prevents them from going directly. So, they need an external path. This is where our electrical circuit comes in. We connect an external circuit to the solar cell. This circuit could be wires leading to a light bulb or a battery. The collected electrons flow out of the n-type silicon. They travel through the metal fingers and into the external circuit. As they flow through this circuit, they can do work. They can light up that light bulb. They can charge that battery. They are providing electrical power. This flow of electrons is what we call an electric current. After the electrons have done their work in the circuit, they need to complete their journey. They flow back to the solar cell. They usually return to a metal plate on the back of the cell. This plate is in contact with the p-type silicon. Here, the electrons can finally recombine with the holes. The cycle is complete. As long as sunlight keeps hitting the cell, new electrons and holes are created, and the current keeps flowing. This process continues silently and efficiently. A single solar cell does not produce much electricity on its own. Each cell typically produces about half a volt of electrical pressure. This is not enough for most uses, so many solar cells are connected together. They are wired in series to increase the voltage. They can also be wired in parallel to increase the current. These groups of connected cells form a solar module, or a solar panel. Many modules can then be linked together. This way we can get enough power for a home, or even a whole town. Section 5. Hurdles on the path to a solar world. While solar power holds immense promise, there are challenges. One major issue is that sunlight is not always available. The sun does not shine at night, obviously, and on cloudy days the amount of sunlight reaching solar panels is much lower. This means solar power generation is intermittent. It is not constant like power from some other sources. We need ways to store energy for when the sun is not shining. Batteries are one option, but large-scale storage is still a hurdle. Another challenge is that sunlight is not spread evenly across the Earth. Some regions, like deserts, get a lot of sunshine all year round. Other regions, especially those far from the equator, get much less sun. This is particularly true during winter months. This uneven distribution means that solar power might be very effective in some places, but less so in others. We need to think about how to share power. Long-distance electricity transmission lines could help move solar energy from sunny areas to less sunny ones. The efficiency of solar panels is also a consideration. Solar panels don't convert all the sunlight that hits them into electricity. Current commercial solar panels typically convert about 15 to 20% of sunlight into power. Scientists are working on more efficient cells. Some experimental cells can reach over 46% efficiency, but these are not yet widely available or affordable. Improving efficiency while keeping costs down is a key area of research. Higher efficiency means we need less space for the same amount of power. Finally, there are political and economic factors. The existing energy industry based on fossil fuels is very large. There can be resistance to change from businesses that benefit from the current system. Shifting to a solar-powered world requires big investments. We need money for research, for manufacturing panels, and for building new infrastructure like smart grids. Overcoming these established interests and finding the necessary funding are significant tasks. Public support and government policies play a vital role here. Section 6. Solar power. Getting smarter and spreading wider. Scientists and engineers are constantly working to make solar power better. As mentioned, the efficiency of solar panels is improving. While today's common panels are around 15 to 20% efficient, new lab records are much higher. The gap between lab performance and commercial products is slowly closing. This means future solar panels will generate more electricity from the same amount of sunlight. This makes them more cost-effective. It also means we will need less land area for large solar farms. New types of solar technologies are also emerging. For example, researchers are exploring materials like perovskites. These could lead to solar cells that are cheaper and easier to make. Some might even be flexible or transparent. Imagine windows that also generate electricity. Another innovation is floating solar farms. These are solar panels mounted on structures that float on water bodies. This could be useful for countries with limited land space. It also helps keep the panels cool, which can improve their efficiency. The potential for global solar power is enormous. If we wanted to power the entire world with solar energy, it is technologically possible today. It would require a lot of land, but not an impossible amount. Estimates suggest we would need tens of thousands to hundreds of thousands of square miles for solar panels. To put this in perspective, the Sahara Desert alone is over 3 million square miles. Only a fraction of such desert areas could, in theory, provide enough energy for everyone on Earth. Even in less sunny places, solar power can still be a good option. Countries like Germany and the UK have significant solar capacity, despite not being the sunniest. While they might produce less power per panel than a desert location, it still contributes. For these regions, combining solar with other renewable sources and good energy storage is key. As solar technology gets cheaper and more efficient, it becomes more viable in a wider range of locations. The sun shines everywhere, even if some places get more direct rays than others. Section 7, Lighting Up the Future, Solar Energy for All. One of the most exciting aspects of solar energy is its ability to bring power to remote areas. Around 1 billion people worldwide still lack access to reliable electricity. Many live in developing countries, often in rural communities far from national grids. For these people, solar power can be a game changer. Small, standalone solar systems can provide power for lights, phones, and small appliances. This is often much cheaper and safer than alternatives like kerosene lamps. Solar energy can truly empower communities. The cost of solar power has been falling dramatically. Over the last decade, solar electricity has become much cheaper. In many places, it is now competitive with electricity from fossil fuels or even cheaper. This trend is expected to continue. As manufacturing scales up and technology improves, solar panels will become even more affordable. This economic advantage is driving rapid adoption of solar power globally. Businesses and homeowners are increasingly choosing solar because it makes financial sense. Remember, solar panels are also very durable. They have no moving parts and can last for 25 years or more with minimal maintenance. This longevity adds to their economic appeal. Once installed, they provide clean energy for decades. This reliability is crucial for long-term energy planning. As we face the challenges of climate change, solar energy offers a clean alternative. It produces no greenhouse gas emissions during operation. This helps us reduce our impact on the planet. The future of solar energy looks incredibly bright. It is becoming more efficient, cheaper, and more versatile. It can power bustling cities and remote villages alike. With continued innovation and supportive policies, solar panels could indeed power a very large part of our world. It is a journey that requires effort and investment, but the rewards are immense. A world powered by the clean, abundant energy of the sun is a future worth working towards. It promises a healthier planet and energy access for all.